So our next speaker is Lior Cohen, and he recently moved to CU Boulder. He was a postdoc of Dr. Dowling.
All right. So first, thank you for the organizers for organizing this wonderful event and to invite me here. My name is Lior Cohen. I'm a research assistant professor at CU Boulder. And before that, let's say I was the last postdoc of John. And today I'm going to tell you about my experience working with John and what I learned from him. Don't worry, nothing to do with physics. And I will try to do it while speaking on quantum LiDARs. So Dowling, if you don't know anything about quantum LiDARs, that's completely fine.
Okay.
And
I will after you're done, right?
yeah, I just wanted to say that. Feels good. All right, so let's start. So I'll start with some introduction, how I met John. So actually I have quite long history with John, almost 10 years. And for some background, I will present something I did in my PhD, which was to demonstrate range-finders and LiDARs with photon number resolving detector. Then I will talk about quantum LiDARs and how we showed that with photon number resolving detectors we can actually do something better than classical detectors, which will be intensity detectors. And at the end I will tell you why I think it's important, and when we get there, that it will be more clear. The title will be more clear. Okay, so let's start. So I started my master degree at 2012, and this paper was published 2 years ago, and my advisor told me, okay, build an interferometer, we have photon number resolving detector in the lab, and just do this experiment. I did that, and then he told me, okay, submit an abstract to conferences. So we got into 2 conferences. One was QIM, and I had a poster, and for me it was quite an experience. That was actually the first time I left Israel. I had to get a passport and everything. So I was quite green, I would say. And I came to the conference and I see John, so with my Israeli chutzpah, I told him, hey John, I'm Lior, I'm a student of Chagai Eisenberg. I implement your proposal for super resolution. Please come see my poster. So I was in the poster session waiting for John, and of course he didn't arrive. So again, I was quite green, so I looked for him and I went to his poster. And of course he wasn't there. So I needed to look a bit further away, and I saw him drinking beers with his friend, and I basically had to take him from his friend and to the poster and show him the poster. So that's my first interaction with John. I showed him the poster mainly after I asked questions and not him, of course. But it was a wonderful interaction, and he, of course, told me, send me an email, I will send you my new paper. And I did that, and he sent me his paper, and 2 weeks later, I got an email from LinkedIn that he invites me to LinkedIn. I didn't have an account. Well, he really went the extra mile to give me good feeling about the work I did, and that's something special about John. So I met him a few times since then, And then I become the OSA president, student chapter president at the Hebrew University. And one program of OSA is that you can invite speakers to your institutes. So I thought, oh, that would be great if I can invite John. So that was December 16. And then we thought, okay, John Dowling is coming. We have to do something special. So I went to Rami Levy, which is the poor Israeli version to Walmart. And for more experience, you can ask Elisha later. And I bought 10 six-packs of beers. So now, Israeli don't drink so much, especially at work. And you can count the number of empty beers over here. It's about 13, maybe a bit more. So we had left with something like 40 bottles of beer, and you can see how happy I am in this picture. And for the rest of the week, what we did is to sit in the kitchen and talk about physics, drink a bottle of beer, talk more about physics, drink a cup of coffee, and repeating the same. So then I thought to myself, wow, that's amazing. You can drink, you can have fun, and you can do physics at the same time. I want to be John's postdoc. But what I got from him is, you're going to graduate soon. You should find a postdoc position. I can help you. And then he started to mention groups. He didn't offer himself. So I'm like, that's not my plan. But after that, he told me, okay, come visit me at LSU. And after 9 months, I came to LSU and I presented the same project that we are going to talk now. Actually, it's almost the same slides. The experimental rangefinder and LiDAR based on photon number resolving detectors, and I present it here because it's relevant to the story. So again, you don't need to know anything, Dowling, about rangefinders. I will say everything now. So the basic idea of time-of-flight rangefinders is to send short pulse of laser to a remote target, to collect it back with optics and to a detector, and by measuring the time it took the pulse to go to the target and back, and by knowing the speed of light, you can detect the range. So that's a simple idea. Now, if you want to do it with very low intensity, very low lasers, low intensity lasers, you basically need to measure single photons. But now when you do it, you have background. And if you do it in daytime, the main source is the sun. So if you're trying to do it with a single photon detector, and again, Dowling, you don't need to know anything about single photon detectors. What you need to know is that it can differentiate between 0 photons and any other number of photons. So it cannot say if you have 2 photons, 1 photon, or 3 photons, but it can say, oh, you have more than 0 photons. So if you try to do it with that, and with this detector, and then you get the pulse from the laser, you cannot distinguish between the light from the laser and the light from the sun. So in this case, you cannot tell when the light from the laser came and what is the range for the target. But now if you do it with photon number resolving detectors, and for those detectors, you can say how many photons are detected. So in this case, you can stop the time measurement only when you get, let's say, 5 photons from 5 photons in the detector. So in this case, you completely reject all the photons from the sun, and you detect only the photons from the laser. So again, this is the picture of rangefinder, but now instead of intensity detector, we just put photon number resolving detector, and that's how it looks in real life. And I really enjoyed to do the mechanical engineering and the optics. So here is the laser, and here we had either PBS, polarizing beam splitter, or beam splitter. It's not that important, and the detector is right here. Okay, so if we want to see the raw data of the experiment, we can just look on oscilloscope and to integrate for some time. And what you can see here is the return from the target, and you can also see the discrete voltage level. So if you have 0 voltage, it corresponds to 0 photon, some voltage to 1 photon, twice the voltage, 2 photons, and so on and so forth. And we also have the measurement of the timer. And actually here we have more than one target, separated by 18 centimeters. And also we did outdoor experiments going out to the field. That's really nice project. I enjoyed a lot doing it. And we measured up to 9 kilometers with 5 microjoule. And it's about 2 orders of magnitude better than what you can do with conventional rangefinders. Okay, so now we have the rangefinder, and we want to make it a LiDAR. So our detector doesn't have the spatial resolution, and somehow you need to add the spatial resolution to the detector. So there are a few ways to do it. One way is just to scan the position of the detector. Another way is to somehow block the entire scene and then release it pixel by pixel. And you can have better and smarter ways to do it, as like a single pixel camera methods, and we did it with compressive sensing. Let me skip about how it works. It's not really important for this talk. And so it's almost the same experimental setup. Now instead of getting the light from the target straight at the detector, now we hit a DMD, digital mirror device. It's a tiny device with millions of micro mirrors on it, and basically we can send the light from the target to the detector or somewhere else. So that's how we implement it in the lab. So again, some basic results. So X, it's hard to see the axis. So X and Z are aligned with the flow. Z is the axis of the laser, and we just illuminated a tilted plastic board, and we were able to see the tilt, which it was a bit surprising. And N is the number of pixels that we used. You can think of a picture, but now it's 3D picture, so every 2D picture is 256, and we actually use less measurement than the number of pixels. That's the idea of compressive sensing. It's not that important for this talk. So up to 6 or 3% of the number of pixels, you can still see the target and the tilted target, but if you take less and less, eventually you cannot see that. You cannot see the target. Also here we had outdoor experiments, and we measured up to a few hundred meters in daylight. And you can see we got a lot of details, the shape of the stones, the tilt of the stones, some bushes. So that's that. So I presented this when I came to LSU. And of course, one of the things that we did is to drink. So we brought some beers, and I think it was bourbon, but we didn't have cups. So my advisor thought it will be smart to drink from the cover of cups, and I thought it's an idiot way to do it. So I came up with a better idea. I finished one beer, and then I put the bourbon inside the beer bottle. And then we were talking, and once in a while I thought I'm drinking beer, so I took loud sips. And I was quite drunk, so I went to the restroom, and I met, when I came back, I met John in the hallway, and I got to him and I told him, I want to be your boss. I want to work for you. So Johnny, before you said that's not the way to apply to postdoc, I'm sure my way is way off. The way to ask someone to be his postdoc. I think that's maybe the only time that I saw John speechless. He didn't know what to say. He didn't know what to say. So he mumbled something, and then he said, I don't think it's a good idea. And the first thing he had in mind was to say, there is not a lot of kosher food in Louisiana, and you're too skinny already. That's what he said. So I was upset with that, and that's the second time I hear no from John. But a month later, he visited again to Israel, and we actually sat and wrote a white paper for a proposal with the title Quantum Technologies that Reject Thermal Noise in Coherent States. You can imagine where this came from. And the first milestone was to show that you can reject thermal photons using number statistics. So we got the grant, and a year later, December 18, I got to LSU. Okay. Need to speed a bit. So let's talk about this project. So I came to John Dowling's group, and he asked me basically to do a follow-up on my previous work and to show why it's working. So I thought, well, this is boring. So John tried to motivate me, and he had this phrase, Nick. You know the golden rule?
Yes, I do. Does anybody else know the golden rule?
So, who has the gold makes the rules. That's the golden rule. Well, it didn't help, so every group meeting he told me, go to the board, present the problem. So I presented the problem. So let's say you have just the background and no photons from the laser. So the distribution is thermal light, which is mainly concentrated in low photon numbers. And this is not the same if you have photons. So the main distribution is where the average photon numbers are. And because of that, we think that taking only high photon number is actually better. It helps rejecting the thermal light. So that's the idea. I presented it in a few group meetings, and John saw that I don't have any progress. Then he did another move, and he told me, Cohen, you help all other students with their project. Maybe Elisha will help you with your project. So he gained two things. One, he knew Elisha will not say no to him like me. And the other one, he didn't talk to me, he spoke to my ego. Do I need Elisha to help me with the project? So that was a smart move. And right after this group meeting, Elisha and I sat in my office and we came up with the calculation of how to do it, and we did something quite simple calculation. So the figure of merit so we want to compare the threshold rangefinder to the classical intensity rangefinder, and the figure of merit that we took is the SNR, where the way we calculate the SNR is that the signal is the output of the detector when you have photons from the laser, and the noise is the output of the detector when you don't have the photons from the laser, from the target. So if you do it with classical detectors, with intensity detectors, the signal is the first moment or the average photon number. So you take the first moment of the distribution with the photon from the laser and you divide it by the first moment of the distribution without the photons from the laser, just the thermal distribution. And for the quantum state, it's quite the same. So the signal is the sum over the distribution from the threshold photon number to infinity, and the noise is the sum over the thermal distribution from the threshold photon number to infinity. And here you can see an example where the average, where the threshold photon number is 2. So the next thing we did, sorry. So now to compare it, what we did is just divided the quantum SNR to the classical SNR, and in any place that we got more than 1, basically you have quantum advantage. So what we have here is the ratio of SNRs as a function of the photons that we get from the target, and the different curves are for different threshold numbers, photon numbers. So this is a theory group. We are not going to do the experiment, but we for sure can simulate it. So the next step we did is to simulate the rangefinder experiment. So we divided the time to 50 slots. In every slot, we put a random photon number based on the thermal distribution. And for 4 slots, we added a random photon number based on a Poissonian distribution, like the laser distribution, with average photon number of 10, 3, 1.5. And you can see the comparison between intensity detection in black and a threshold detection of 5 in dashed blue. So, and of course, that agree with the analytical expression that we got. So then I asked John, John, we got those nice results. Where do you think we should send it?
Send it to PRL.
Send it to PRL. I told John, well, this is nice, but I don't think it will go to PRL. If it goes to PRL, I will resign from science. And guess what? So months after that, it doesn't matter who we met, what was the conversation, he told that. Like, we had the results, he said that if it goes into PRL, he will resign, and he didn't do it. So I lost my pride. Let me tell you why I didn't lose my dignity. So let me tell you why now I think it's important. And that is based on 2 points. One is that we were able to prove that this is optimal for ranging, and the other point is that this is actually optimal to an entire family of other applications. So I don't have a lot of time. Let me try to compress it even more than what it is right now. So to to do that, we went to quantum information theory. We used state discrimination. If you have the target or you don't have the target, you get two different states. If you can discriminate between the state, you can basically say if there is a target or no. And the proof, I don't, of course I don't want to go all over it, but basically, because you cannot use the phase, the best you can do is photon number detection, and because of the distribution and where because the distributions intersect only in one point, then you get that threshold detection is the best option. Okay, so usually when we talk about improvement of sensor or quantum improvement of sensors, we think of using entanglement or squeeze light or something like that. But if we have an application with high loss, we cannot do that. So the only option that we have to improve detectors in this case is to use quantum detection. And again, if you don't have the access to the phase, the best thing you can do is photon number detection. And actually now we are trying to use photon number detection for fluorescence imaging, because in this case you have both lot of loss and you don't have any phase information. So for conclusion, again, I don't want to talk about physics, but let me just give you take-home messages, not from me, but from John. So first, never give up. I think Irina said it before me, but I say it mainly to students. You hear no, don't be okay with it. Try to understand why you got the no, and try again. Don't underestimate the potential of your work. We got very positive reviews, and I thought, oh, I just got lucky with reviewers. I don't think that was the case. I think we really got something, maybe we had luck, but we got something special and I didn't appreciate it. So don't do that. For professor, so look for the potential. So I interact a lot with John, and sometimes he spoke with some student. I couldn't say why. I didn't see anything interesting about the work, and I think one strong quality of John was to see the potential. And if I'll be honest, if I were John, I wouldn't hire myself. Okay? Somehow John was able to see the potential in me, and I think I did quite good as a postdoc. And the other point is use your influence. So another story, I came to John, and so John used to complain about him being needed to write tens of recommendation letters a day. So one time I told him, John, I have a friend, he wants your recommendation letter for green card. And he told me, yeah, sure, no problem. And he told me, I know that in my position, in a few minutes, I can make someone's life much easier. So that's one thing. And the other thing, my first interaction with John had a lot of influence on me and made me work harder. And you know, you want to go to conferences and drink beer with your friends, but there are young students that are waiting in the poster session, and if they get, and they know you, and if they get nice words from you, that will impact them. And I think my work was okay, but John went beyond, and gave me good feeling, and it had a lot of impact on me. So use your influence. Do I have 1 more minute? I want to tell John's story.
It's fine.
Yeah? Okay, Ryan is here? No. So Ryan talked about being a target of John in jokes. So I usually was the target, and of course I didn't like it. It was embarrassing talking about my religion and everything, but I can see why he did it. And Nick, I know now we're trying to make John a saint, but let's give him the benefit of the doubt. I think he did it, he embarrassed us to make us closer. Because when you speak about your weaknesses, you don't eat, you're religious, or not just weaknesses, your personal life, then you can be closer to people. So that's why I think he did that. So I was his target, and he got really interested in my beliefs, and I knew it's going to be more ammo for John, but I really think he truly was interested in that. So I told him a lot of details about what I can do and cannot do. So I told him that I cannot write during Saturday. And he got really excited. He told me, you know, for years I'm trying to buy the old-fashioned chalkboard, and the department they don't allow, they don't let me. And if you can tell them that you cannot write on regular boards, that will help me. So I told him, John, but in Saturday I cannot write with chalks as well. So he told me, so maybe you can find a loophole. So I think Jews are good in finding loopholes. That's why you have good Jewish attorneys. But I didn't want to play that and try to find a loophole so John can have a chalkboard. But yeah, so that's my John story. Thank you for listening, and please ask me.
Great. Any questions for Dr. Cohen? All right. So single photon detectors, they can be used for any experiment? They can be used for any experiment, anything in laser, like optics?
Yes.
Okay. Also, I did have a question about that. Where the habit you got of asking people to go up to the board and ask their, or like give them, write their problems down. That came from John.
Oh yeah, it didn't come from me. I wanted to do that. No, but yeah, that was his.
He would insist, Eliza, write your problems on the board. Anything?
Yes. Could you say thank you for the wonderful talk? Could you say a little bit more about the photon number detectors that you use?
Okay. Do I have? I don't have backup slides for that. So we used Hamamatsu's forgot the name. Silicon photomultipliers. So basically, you take a single photon detector, which is just silicon with the avalanche detection, and then you make ditches. So then you have elements, and because of the ditches, the avalanche is more local.
Right. Okay. Yeah. So it's like you're splitting up your signal into like regions when you trigger. Okay. Thanks.